4.543 billion years ago, the Earth formed. Earth formed 4.6 billion years ago. It was very different from today's Earth. Earth began as a hot ball of rock. Earth began as a hot ball of rock. Stay with me now. Focus, okay? 3.9 billion years ago, it cooled down and it began to rain on the rocks. Billions of years of torrential rains created the oceans. Earth Science book right there. Earth started out as a ball of very, very hot liquid. The liquid was mostly made of two elements called oxygen and silica. There were small amounts of other elements too. In fact, it was a mixture of almost every element in existence. From theconversation.com. Downloaded in February here. After a few 100 million years, the temperature of Earth reached 2,000 degrees, the melting point of iron, and Earth's core was formed. So the Earth is still a hot ball of rock. Earth formed 4.54 billion years ago, 1/3 the age of the universe. Swirling in the waters of these oceans that are forming as it rained on the rocks is a bubbling broth of complex chemicals. Progress from a complex chemical soup to a living organism was very slow. Is that saying it slowly came from a rock? Yeah. It is in these oceans, 3.5 billion years ago, scientists believe the first living organisms appeared. Downloaded in March of this year. The oceans formed 3.8 billion years ago. Remember, Earth formed 4.6. Had to cool off for a while. It was a really hot ball of rock. Cooled off for a long time. And it rained on the oceans, okay? The oceans formed. And it was the hot soup. Scientists cracked the 40-year-old DNA puzzle and point, hot soup is the origin of life. The primordial soup of where life began on Earth was hot and not cold. From Science Daily, okay? Primordial soup, prebiotic soup, is the hypothetical set of conditions present on Earth 4.2 to 4.0 billion years ago. Okay, let's see. Downloaded in February. What does primordial soup consist of? The seas and atmosphere as they existed on Earth before the existence of life, consisting primarily of oxygen-free gaseous mixture containing chiefly water. Oxygen-free. Doesn't water contain oxygen? I think it's H2 something or other. Yeah, okay. Hydrogen, methane, ammonia, and carbon dioxide. Dioxide means, you know, two oxygens? Okay, anyway. Primordial soup from dictionary.com. Life on Earth first bloomed around 3.7 billion years ago, when chemical compounds in the primordial soup somehow sparked into life. Now, stay with me. The primordial soup came from the rocks getting rained on. So the Earth began as a hot ball of rock, then it rained on the rocks and turned them into soup, and the soup somehow sparked into life. I didn't make it up, okay? Primordial soup theory suggests that life began in a pond or ocean as a result of the combination of chemicals from the atmosphere and some form of energy to make amino acids, the building blocks of proteins, which would then evolve into all the species. The first self-replicating systems must have emerged in this organic soup. They've been teaching this for a long time. I got textbooks from the 80s, 90s, 2000. Yep. So 13.772 billion years ago, there was a big bang where nothing exploded. It spread out everywhere. And a whole bunch of the nothing got together and made Earth 4.6 billion years ago. It was a hot ball of rock, really hot. Okay, all the nothing turned into a rock. And then it rained on the rocks for a long time, and they cooled down enough, and life appeared 3 billion years ago. Yes, guys, you do think you came from primordial soup, and the primordial soup came from the rocks getting rained on. So we came from a rock. How about this one, downloaded today? This is April 29th, today, downloaded a couple hours ago. Earth formed 4.54 billion years ago, 1/3 the age of the universe. Okay, let's see. When the solar system settled into its current layout 4.5 billion years ago, Earth formed when gravity pulled swirling gas and dust in to become the third planet from the Sun. Like its fellow terrestrial planets, Earth had a central core, a rocky, which is the root word would be rock, okay? A rocky mantle and a solid crust. I'm trying to use small words so you guys can get it. In-depth Earth, NASA solar system. Earth formed 4.5 billion years ago. Scientific American. Continents and oceans encircled by oxygen-rich atmosphere support familiar life forms. Yet this consistency is an illusion. They go in this article talking about life coming from the soup, from the rocks that got rained on. How about Sutori.com? 4.56 billion years ago. Oh, we got to talk to, they got to get together on their numbers here, but that's okay. The Earth began and it was a hot ball of rock. This is what is taught. Here's a HumanOriginProject.com. It talks about 4.6 million years ago, the Earth formed. Well, they have a little problem here. It should be billion, guys. Get your, why don't you make it trillion, just to give you enough time, okay? Quadrillion, okay. Downloaded today. The earliest known life forms on Earth are putative fossilized microorganisms found in hydrothermal vent precipitates that may have lived as early as 4.28 billion years ago. Relatively soon after the oceans formed, wait a minute, the life came after the oceans formed 4.41 billion years ago. And not long after the Earth formed 4.54 billion years ago. Is this teaching life came from the rocks? Am I making it up, or is this what they're saying? Okay. How about from Wikipedia? If life evolved in deep ocean near a hydrothermal vent, it could have originated as early as 4 to 4.2 billion years ago. If, on the other hand, life originated at the surface of the planet, so is it deep water or shallow water? We don't know. Need more government grants to go find out. A common opinion is it could have done so between 3.5 and 4 billion years ago. Either way, it came from the oceans, which came from the rocks.
They're dazzling, priceless, at times even glowing.
How can one not fall in love with rocks and minerals? I mean, the colors, the shapes.
And they're the building blocks of modern civilization.
We wouldn't have televisions, we wouldn't have automobiles, we wouldn't have buildings without the mineral riches that we have.
But could rocks and minerals also solve the greatest mystery of all time, the origin of life?
The rocks we pick up tell a story that life couldn't have occurred without rocks.
Could cold, lifeless stone hold the key to every living thing on Earth? From Australia to Morocco, Nova goes around the world and back in time to investigate the origin and evolution of life.
Look at a rock and you think, well, nothing. But this holds the signature of life.
From its first spark
people were saying they made Frankenstein in a test tube.
To the survival of the fittest.
These were immense creatures, sharks that may have been 50 or 60 feet.
Was it the secret link between rocks and life that made the difference? Life's rocky start, right now on Nova.
Well, up until we have a situation where we have a warm, wet, rocky planet called Earth, where we can pretty well understand how we can gather together and form a little parcel of interacting chemical substances that we know are essential for biochemistry. We can even maybe arguably explain how these come together to form crude metabolic cycles, RNA, DNA, other things. But there's a discontinuity of explanation when it comes from explaining how we take that systems chemistry and from it we get life. And life must have spontaneously arisen 3.5 billion years ago, if not earlier. And we know of no situation in the entire history of this planet where life has ever since come from anything other than life. So life has simply not spontaneously arisen, as far as we know, at any subsequent time.
Hawking has stated that he believes life originating on other planets is perfectly rational because our galaxy is just 1 out of 100 billion. And although he admits the chance of life arising spontaneously is very small, he does not feel that this is a problem for his theory. It's like winning a lottery, he claims. Although the odds are astronomical, most weeks someone hits the jackpot. Others have claimed that, like the lottery, although the odds that you will win is very small, the odds that someone will win is almost a certainty. How is it that with the incredible odds against winning the lottery, someone always manages to do so? Well, look at it this way. Say we have 5 cards. All but one have "you lose" written on them, and one card says "you win." All the cards are shuffled face down, and one person draws a card from the top. The odds of that person winning are 1 in 5. But say we have 5 people drawing a card. The odds are still 1 in 5 for each person to win, but the odds are also 100% that someone will win. That's all fine and good for the lottery, but what are the chances of life arising spontaneously somewhere in the universe? Life is very complex and made up of many components. Take a protein, for instance. Proteins are what make up the structure of living cells, and without them, we would not exist. They are responsible for such functions as catalyzing metabolic reactions, DNA replication, responding to stimuli, and transporting molecules from one location to another. Proteins differ from one another primarily in their sequence of amino acids. They are, at their simplest form, a chain of amino acid residues that can vary in lengths from just 20 amino acids to over 30,000. And there are 20 different amino acids found in proteins. Each link in the chain could have any one of these amino acids. The typical enzyme is around 200 amino acids long and is a form of a protein that catalyzes metabolic reactions. It is essential to life, so we will use it as our basis to determine the odds of a protein arising spontaneously in the universe. You can think of a protein like a password. A password is more secure the longer it is. Hackers try many methods to crack passwords. If a hacker can't get your password by an easier method, they may resort to what is called brute forcing. This is the least preferred method because it can be long and processor intensive and may even be impossible. And even when brute forcing a password, a hacker doesn't do so aimlessly, but directs his blows so as to be more likely to get a hit. Instead of trying random characters, they use passwords that are statistically used more frequently than others. Then, if those don't work, they try the lesser likely passwords. To try to brute force a password using random characters could prove impossible if the password is too long, because there wouldn't be enough time to try all the possible combinations of characters in a person's lifetime. To illustrate, take these 4 balls. Imagine this is a password. If you look at this number, we see 9,999 possibilities. But really, since we are using 02, we actually have 10,000 possible combinations. Another way we could figure this is by taking the number of possibilities for each ball, which is 0 through 9, so there are 10, and putting it to the power of 4. How does this relate to a protein? Well, imagine these balls are amino acids, and instead of 10 possible digits for each ball, there would be 20. Now, if our chain was only 4 amino acids long, then there would be 160,000 possible combinations of amino acids. If a hacker was attempting to crack this password at 1 attempt per second, that would be 60 attempts per minute, and it would take over 44 hours to go through all the possible combinations. But what if we add just one more amino acid? That number increases exponentially from 160,000 to 3,200,000. And now it would take our hacker over 1 month to exhaust all the possibilities. Add another amino acid and the number jumps to 64 million possibilities. And the amount of time it would take our hacker would be over 2 years. Add just 4 more amino acids for a total of 10, and it would take over 324,000 years. Now, keep in mind that the average enzyme has around 200 amino acids, so you can see the number of possible combinations would be incredible. But does that matter? After all, there are at least 100 billion galaxies, all containing billions of stars and planets. So surely there are enough planets out there, at least a few of them would be able to produce an enzyme, right? I mean, after all, Stephen Hawking is an expert, and surely he has done the math, and wouldn't just make a hasty generalization, correct? Well, let's actually do the math and see. First, we must find out how many planets there are. We obviously can't get an exact number, but scientists have estimated less than 6 trillion to be in the habitable zone. The habitable zone is the region around a star in which a planet can orbit and sustain liquid water. Now we know that not every planet in the habitable zone is able to support life. There are many factors involved, but we will be generous here and assume that they all can. In fact, we will be even more generous and assume that there are many more planets than estimated. We will include all the estimated planets in the universe, even those that are not in the habitable zone. That number is estimated to be 10 to the 24th power. For our illustration, we will think of our planets each as a hacker trying to decode a protein. And the odds of getting an enzyme are 20 to the 200th power. But there's one more thing that we need to consider. Looking back at our illustration of the 5 cards, we just showed that there is only one possible winning card. But what if there are more than one? Say we have 3. Then the odds are now 3 out of 5 chance of winning. Much better odds. So we need to know how many enzymes there are to determine the odds of getting a hit on one of them. Currently, there are around 70,000 known enzymes. So for good measure, we will increase that number to 1 trillion just to be safe.
Wow! Oh, yeah.
That will give us the odds of 1 trillion out of 20 to the 200th power of getting a hit. How big is 20 to the 200th power? It is equal to 1.6 times 10 to the 260th power, or to better illustrate, a 1 followed by 260 zeros. Scientists estimate the total number of all the atoms in all the known universe to be just 10 to the 80th power, so we can see this number is huge. So we know the odds are 1 trillion to 20 to the 200th power. Let's reduce this to the lowest common denominator. We do this by dividing both the top and bottom numbers by 1 trillion. This gives us this new number, which can also be shown in scientific notation like this. Or to give you a better idea, like this. So that means in order to get a protein, each hacker or planet has a 1 out of this many chance of winning. These are the odds. Now just like the hacker who attempts 1 time per second, how many times are our hackers or planets going to try per second? Well, to be generous, we will assume that every planet is made up entirely of amino acids, and they are constantly swirling and linking up with each other. We'll use the Earth as a model and assume each planet is the same mass as the Earth. The Earth has an estimated 1.33 to the 50th power atoms. We will round that up to 10 to the 51st power. Then we will divide that by 200 to see the total number of possible enzymes that can be made at one time. Now we will assume every second this number of proteins are formed on every planet. But how long will it take to make a functional enzyme? Remember, each planet is nothing but a pool of amino acids. We will multiply 5 times 10 to the 48th power by the number of planets in the known universe to see how many attempts total are being made. Then we divide the odds by our new number. This gives us the maximum number of seconds it will take to exhaust all the possible combinations. How long is that many seconds? It is equal to this many years. Unfortunately, the universe is only estimated to be less than 15 billion years old. Here's a side-by-side comparison. The age of the universe compared to the age the universe would need to be to acquire one enzyme. So we can see the age of the universe is significantly insufficient to have actually made even one enzyme, yet alone to have done this multiple times on the same planet within the short time span it had to do it in. We must remember, if a hacker was trying to crack this code, he would not try the same combination more than once. But in nature, there wouldn't be that restriction. Granted, nature wouldn't need to go through all the possible combinations before it got a hit, but even if it took only 10 to the 100th power of the time, there still hasn't been enough time to do it in. To me, this is overwhelming evidence that for life to occur spontaneously, it is impossible. It had to have had direction from an intelligent force. Even if the universe had unlimited number of planets, this would still be impossible, because once a planet made one enzyme, it would have to win that same impossible lottery at least 250 times in a row to make a functional living cell. Have you ever heard of someone winning the lottery 250 times in a row? At least you would have a better chance at winning the super lotto than this lottery. But then it would have to do even more impossible odds that I'm not even covering in this video. And there's even more to a protein than its sequence of amino acids that give it its properties. It has to fold onto itself in a specific way. So that just adds to the complexity of it. Not to mention left and right-handed proteins, and there are many other factors. So there's just too many factors to consider. And to me, it takes more faith not to believe in a creator than to believe in one. And that's the science. I've had this discussion with others before, and they acknowledge this conundrum, but they don't offer any explanation for why they believe there is no creator. They simply state that although we don't understand everything now, that one day in the future, far in the future, we'll figure it out someday. Well, my friends, I'm not waiting on future evidence that hasn't presented itself yet. I'm going by the current evidence. If someone can prove to me something different, then I'll believe that. But until then, I will believe what the evidence right now tells me.